So let's take a look at a first example of calculating the probability of type 2 error. Say we're testing internal combustion engines with bearings made out of copper lead. We want to measure the amount of wear on these bearings after a fixed amount of mileage. We collect a sample of 8 engines, and Y bar for that sample is 3.72, and a standard deviation of 1.25, both of which are measured in 10,000ths of an inch. So let's say that our hypotheses are these. Okay, we're going to key in on greater than 3.5. Okay, so we want to know, is mu, the mean population of this wear, is it greater than 3.5? That would be in the alternative. The greater than statement would have to be in the alternative. The equality statement must be in the null. Okay? And we want to know the probability of type 2 error if the true mean, okay, let's say this, the true mean is 4. Okay, so we collected a sample of 8 engines, so n equals 8. And we found from that sample the Y bar, the sample mean, which was 3.72. And we found a standard deviation of 1.25. Okay, so one thing we might look at here, yeah, 3.72 is quite a bit above 3.5. However, the standard deviation is kind of large. Okay, so we could go through go through the test of hypotheses, but we're probably not going to be rejecting this null just based on how big that standard deviation is. Okay, 3.72 is actually pretty close to 3.5 when you account for variability in sample size. Okay, but that's not really what we're interested in. What we're interested in is the probability of type 2 error when the real mean is 4. Not 3.5, but 4. That is, we're really pulling our sample from a distribution whose mean is 4. So let's draw this out. Okay, so here is our hypothesized distribution. Okay, and this is on the y-axis. Here is the hypothesized value 3.5, and up here, beyond some value, we would reject the null. Okay, and let's conclude that we're wanting to draw conclusions with 95% confidence. Okay, so this area up here is going to be 0.05. Okay, we want 95% confidence, alpha of 0.05. Okay, but here's what's really going on. The mean is really 4. Okay, the mean is really 3.5 plus some value of delta, such that the real mean is 4. This is the real distribution of what's going on. That's really what we pulled our sample from. Okay, the population is this green distribution, which is supposed to be centered at 4. Okay, so what's the probability of type 2 error in this case? What's the probability that we fail to reject H0, given that H0 is false? Okay, H0 clearly false. Okay, this is not a true statement. The mean is something greater than 3.5. Clearly, this H0, this null here, the null hypothesis, is false. What's the probability that the sample evidence doesn't tell us to reject? Well, that would be when our sample mean lies down here. It lies in the non-rejection region, but underneath the green curve where we pulled our sample from, right? Remember, this is what's really going on out in nature, this green distribution. That's where we pulled our sample from. What's the probability that we don't reject the null when the null is false? What's the probability we don't reject the null when the mean is really 4? It's when we pull the sample that lies in the non-rejection region. Okay, but we're pulling the sample from the green distribution. Okay, so first we need to find out what's this critical value, not on the t-axis, but on the y-axis. Okay, so let's isolate isolate that this y-axis, but we'll convert it down to a t-axis. Okay, so let's do that over here. Okay, here's our t-axis with degrees of freedom, 8 minus 1, 7. Okay, and we want an upper tail, a rejection region of 0.05. So what is the critical value here whenever we want 0.05 in the upper tail? As it turns out, that value is 1.895. Okay? Now typically we work with the t distribution, right? We would draw a conclusion about a hypothesis test here. But we want to know, what is this value here? Okay, we want to know what is the critical value, but in the y space, not in the t space. So we need to convert this now to the y distribution. So what is this value on the y-axis? Okay, remember, y-axis now has mean of 3.5. This is our hypothesized value. What is this value here that has 0.05 in the tail? Okay, we can do that. We've got an equation for that. That is the t-score equation. T is equal to y minus mu over s over root n. Okay, we know the value of t, 1.895. That's equal to some value y. We don't know what this value y is. Minus 3.5 over s, 1.25, over root 8. Okay? So all we got to do is multiply this over here, add that over there, and we can solve for y. As it turns out, this value of y is 4.337. Okay? This value right here is 4.337. Okay? So essentially what we're saying, and we don't do this whenever we just answer hypotheses directly, but what we're essentially saying is if our sample mean is less than 4.337, we don't reject the null. If the sample mean is greater than 4.337, we reject the null. That's essentially what we're saying right here. Okay? Because we're accounting for variability, sample size, confidence, all of that. If this value, if the sample mean lies out here, then we're going to reject the null. Okay, so now we've got where the rejection region is on this axis. So now we just need to find out what's the probability below this value on the green axis. Okay, the green axis, or the green distribution, that's where the area we want to see. And we want to know what's the probability less than 4.337 underneath the green distribution. So let's do that. Here's the green distribution. It's also on the y-axis. It's got a mean of 4. And here is 4.337. 4.337. And we want that area right there. That is beta. Okay? So this is, again, straightforward to do, right? All we have to do is convert this to a t distribution. But this is what our mean is. Okay? So let's do that over here. T, 4 degrees of freedom, 7. We're going to convert this right here to a value on the t-axis and find the area. Okay, what's that value? That's t equals 4.337 minus 4 divided by s over root n, 1.25 over root 8. Okay, and if we work that out, we should get a value of 0.763. Okay, that area right there is beta. That's the probability of type 2 error when the real mean is 4. Okay, so now we can do that. We can go look that up in a t-table, or we can look up something close to it. Okay, and so what can we find? Well, as it turns out, if we look this up in the t-table, the best thing we're going to get here is 7.763. The closest we're going to get to that for degrees of freedom 7 is a value 1.415. And that's associated with 0.1 in the upper tail. Okay? So we know that, we know what? We know that this area right here, this is the area we're interested in, all the way down. Okay? we know that that area must be in between 0.5, okay, and 0.9. Okay, so our value right here lies in between 0 and 1.415. That must mean that the area below 0.763 is between 0.5 and 0.9. Okay? That's a pretty high p-value. Okay? The probability that we fail to reject the null when the mean is actually 4 is very high. Okay? And why is that? Well, we have a pretty large standard deviation. We're probably not going to be able to detect a shift between 3.5 and 4. Okay? That's really not a very big shift to detect whenever the standard deviation is that big. So odds are we're not going to be able to detect that difference, that change from 3.5 to 4. Okay? That's why our p-value is this big. So, I'm sorry. This is not a p-value. This is beta. That's the probability of type 2 error. I've been saying the right thing. I've just been using p-value instead of beta. Okay? We're probably not going to be able to detect a change from 3.5 to 4 because our beta is so big. Okay? And that's because this standard deviation and this sample size, the standard deviation is quite big, the sample size is quite small. We're just not going to be able to tease out that difference between 3.5 and 4. Therefore, beta is quite large. Okay? The probability of type 2 error lies between 0.5 and 0.9. Okay? We could also use Excel to find this. Okay? If we use Excel, we use the t-dist function. Okay, remember that the t-dist function wants a value on the axis value. It wants a degrees of freedom, and it wants whether the test is a one-tail test or a two-tail test. Okay, a one-tail area or a two-tail area. Well, this is just a one-tail area, but it's going to give us this thing up here above 0.763. So if we find this value for 0.763, degrees of freedom 7, a one-tail upper tail, it's going to give us the area 0.235. 0.235. That's this area up here. Okay? We want 1 minus that. Okay? 1 minus 0.235, which is 0.765. Okay? So if we wanted a very specific value of beta, it is 0.765. Okay? The probability that we don't detect when the mean is actually 4 is quite large. Okay? We have quite a large value of type 2 error. One other thing I wanted to point out here is that all we're testing for is whether or not the mean is something other than the hypothesized value. Okay? We have to have a very specific mu0, mu0 plus delta. Okay? We could calculate a different value of beta for different values of mu0 plus delta. We have to have this in order to calculate beta. And we're assuming that only the mean changes, not the standard deviation. So we assumed the standard deviation here is the same as the standard deviation here. Only the location on the axis changes, not the dispersion. Okay? That allows us to calculate this value of beta, or this set of bounds for beta. We'll do another example to try to reinforce these ideas.